roll here. Okay.
Thank you, Nicole.
Yes, thank you, Nicole. I'm pleased to introduce our speaker, Dr. Mahalingam Balasubramanian. And he is the leader of the Emerging and Solid State Batteries Group in the Electrification and Energy Infrastructure Division at ORNL. The division names have gotten longer over the years. He will speak on battery research at ORNL, and his lecture title is Electrochemical Energy Storage, from Animal Electricity to Electric Vehicles and Beyond. Born and raised in India, Molly is a distinguished R&D staff scientist at ORNL. He has his PhD in physics from the University of Connecticut at Storrs. Prior to his current position as group leader at ORNL, he worked at Argonne National Laboratory, where he served as physicist and beamline scientist with the spectroscopy group in the X-ray science division at the Advanced Photon Source. At the APS, he collaborated with Argonne researchers, team members of the Joint Center of Energy Storage Research, which is a DOE energy innovation hub, and also with groups from other national labs and universities on fundamental questions in energy sciences. Working with others, he conducted research focusing on electrochemical energy, storage systems, hydrogen storage materials, solvation structure of ions in aqueous and non-aqueous solvents, and electrocatalysts. Please join me in welcoming Molly, who will enlighten us on the status of research on advanced batteries.
Please leave a message after the tone.
Thank you all. Good afternoon. I'm Mahalingam Balasubramanian. I should first thank the organizers, Carolyn Krause, Herb Krause, and others for inviting me here. It's such a privilege to be among you all, so distinguished people who have worked at ORNL before or in other places. It's quite a privilege to be here. Today, I'll be talking about the work that is done predominantly in my group by the terrific staff, very talented staff in my group. It's a very diverse group with people with background ranging from chemistry to material science to mechanical engineering to electrical engineering to physics. So there is a wide variety of skill sets that is there within the group. And the science of batteries requires a very broad interdisciplinary program to do it. And I'm so lucky to work with this wonderful team here from whom I learn a lot. I should say that I hope that I will do full justice to the incredible amount of work, which is very different from the kind of background that I had that I'm doing here. And hopefully I will give you some view of the vision of our group and what we do in our group. We all know that to reach the climate goals that has been set worldwide, it is critical that we have to wean ourselves out of fossil fuels, or at least minimize our dependence on fossil fuels. In order to do that, renewable energy has to have significant penetration in our electric supply. Of course, the sun is not there 24 hours a day in all the places, and the wind doesn't flow all the time, and geothermal energy is not available in all places. So energy that can come from renewable sources has to be stored and used in such a way that we can make good use of renewable energy. So it is generally accepted now that electrochemical energy storage based on batteries, for example, is going to be critical to any future penetration of renewable energy. And the sectors that need to, where there can be significant changes so that emission can be reduced, detrimental emission can be reduced, correspond to things like electricity production itself needs to be cleaned up. So the electric grid has to be deeply decarbonized. transportation, whether it is light duty transportation or just personal transportation, all the way to transportation, which involves airplanes and things like ships, maritime applications, have to be decarbonized. Additionally, there are very niche areas in defense where electrochemical energy and the deliverance of energy at the required time is critical to the national security of our country. So electrochemical energy is going to be critical going forward in all sorts of different ways. So having said that, I just want to start with what at least science historians consider as when electrochemistry and electrochemical phenomena has been utilized or made use of by humans. Among the first examples one sees is that of Louis Galvani, who was able to show that when you touch electrodes to a frog, and if the electrodes are made with two different materials, the leg of the frog would twitch. And at that time, in 1786, when this happened, Galvani was trying to make a link between this, between electricity and basically animation. That is something or life. So we all know, we have all heard of Mary Shelley's book, The Frankenstein. And apparently this finding from Galvani was quite popular among the literary and the intellectual circles. And so perhaps what she wrote was, at least in part, based on what Galvani had found out. Of course, we now know that, well, in fact, soon after, Volta did not believe that this could be completely something where you're animating life, and that could be something different. Although Galvani did not get it right as far as electricity and animation is concerned, it is the foundation for modern electrophysiology. We all know that the body and the brain are essentially electric machines. When we go get an EKG done, for example, there are electrodes that are placed, and the response that is coming from small electrical signals is what gives rise to the signals that we see in an electrocardiogram. So, of course, this was one of the foundations for electrophysiology. So Volta, what he immediately did was to figure out that you don't need a biological entity to be involved in this process. And one of the old devices that came in around 1800 is this famous Volta pile. This Volta pile was the first battery where there are two electrodes, one with silver and the other one with zinc. And there is a paper or a cloth which was soaked with brine, which acted as the electrolyte in the system. So this thing was, at that time, was, if you read up about it, it says that it was considered as a construction of an apparatus of unfailing charge and of perpetual power. So this is considered to be the origin of electrochemistry, where the ability to get a continuous current was first shown. It also showed that one might be able to convert chemical energy into electrical energy, and one can control chemistry using electricity. So this experiment is often considered, historically, the science historians consider it as the birth of electrochemistry. From there on, batteries and the field of electrochemistry has gone tremendous progress. Electrolysis of water to all the way to Faraday's laws. These were all done in the early 1800s. And rechargeable batteries started making appearance with the lead acid battery. We still use this lead acid technology in our cars. It is the starter battery that is there in the cars, right? And then there has been nickel cadmium battery, nickel metal hydride battery, and so on. The battery that is now most ubiquitous, it is there in all our devices, in our cell phones, in our laptops, in our power tools, and so on, is the lithium-ion battery. The lithium-ion battery was has a long history. It was there were three gentlemen, John Goodenough, Stan Whittingham, and Akira Yoshino, who together, based on all the work that they had done, brought about the lithium-ion battery. In fact, a lot of the early work on these oxide systems that are used in these batteries was funded by the Department of Energy. So the Department of Energy played a fundamental role in how the lithium-ion battery as we know today exists. For this great work that came out and for the the amount of technological advance this has allowed, the discovery of the lithium-ion battery has allowed, a Nobel Prize was given to it in 2019 to those three gentlemen. So what is this lithium-ion battery? It's any battery essentially has two electrodes. It has two electrodes, a negative electrode usually called as an anode, which tends to be, in the case of a lithium-ion battery, a graphitic-based system mostly, and a cathode, which in this case is a transition metal oxide. So essentially, and in between these two is an electrolyte and a separator, which separates the two electrodes. During the process of battery, when this material is charged or discharged, lithium ions go back and forth between these two intercalation hosts. And when lithium ion is put in or taken out, there has to be a redox process which takes place in these electrodes. And to compensate for the positive charge of a lithium, there has to be an electron in the outer circuit. Either electron while charging, the electron is given to the system, or while discharging, which is what the battery useful work, like powering up a laptop, for example, is when the electron comes the other way. So the charge and discharge reactions involves lithium transport inside the battery and electron transport in the external circuit. So during a discharge, for example, in this case, is this famous lithium cobalt oxide, which was discovered by as a battery material by Professor Goodenough, and carbon, which is the intercalation compound. So you can write these reactions that take place in these two parts using these half reaction models, where a lithium C6 goes to carbon and a lithium, and at the cathode you have the lithium cobalt oxide, in this case with lithium of around 0.5, going to lithium cobalt oxide. And it is the difference in the electrode potentials of these two half reaction which yields an effective operating voltage. In this case of a lithium-ion battery with a lithium cobalt oxide cathode and a graphitic anode, in an organic electrolyte, you get an operating voltage of around 3.7 volts, which can then be put together in these packs to increase the voltage and to deliver a huge amount of current as required. So that is how a battery stores and generates electricity. And it turns out that most of the materials used in present-day lithium-ion battery use critical elements that are not cheap, is not available easily, and is produced sometimes in places where we have geopolitical tensions. So diversifying the source from which we get these materials and diversifying the chemistry is critical if we are going to have mass deployment with very demanding applications. Diversification becomes very important. So there is a lot of work which is going on in figuring out how to do that. And in the group here at Oak Ridge, we do a lot of emerging batteries where we try to do new battery chemistries, try to understand new battery chemistries, and to do solid state batteries. Oak Ridge has a very long history in solid state batteries in the main campus. I work mostly in the Hardin Valley campus. At the main campus, there is a very long history of solid state battery development. And in fact, the thin film solid state battery was pioneered at Oak Ridge in the 90s. So it's natural for us to do a lot of battery research at Oak Ridge. And the kind of work that we are doing is for two different sectors: the transportation sectors, where we are trying to develop batteries for transportation, and grid decarbonization. So for the sort of goals that is there for this is that the DOE wants to bring for electric vehicle batteries the cost to about $80 per kilowatt hour. Right now, it's probably around $135 for a kilowatt hour. In the US, people drive quite a bit and they drive long distances. So the batteries that we want in a place like the US should have a range of about 300 miles. So it's somewhat comparable to what we get out of a gasoline internal combustion engine based vehicle. Furthermore, when we go to when we go to fill up our gas, we normally can do it in 5 to 10 minutes. So a reasonable charge time for an EV battery should be of the order of 15 minutes or less. So these are quite demanding sort of metrics that has to be reached in batteries. So we have to enable fast charging. As I said, we have to be using materials where we don't have either which is quite prevalent at the core in the crust of the earth. We want to go away from things like cobalt. So in the near term, the approach has been to use nickel-rich material. It turns out that lithium nickel oxide is also can be used as a battery material. So there is an approach that has been taken and to go towards nickel-rich materials. However, in the long term, about 5 years or so, one would expect that we would go on to even more earth-abundant materials such as manganese and iron, which is present in the crust quite a bit. So if you look at the sort of EV targets that you have, the number here is about 350 for the specific energy, and volumetrically it's about 750. So it's quite hard to get these with regular lithium-ion batteries. In order to be able to do it comfortably, one possible route is to use solid-state technology combined with a lithium anode. This can meet or exceed the requirements for EV. And additionally, we all know that lithium-ion batteries we often see in news where is very prone to catching fire. So it is critical that safety be an integral part of development of any battery technology, and solid-state batteries potentially can have good safety characteristics. So there is a lot of work that we do both in the field of lithium-ion batteries itself and in the field of solid-state batteries for transportation application. The other sort of work that we do a lot in our group and in Oak Ridge in general is towards trying to get energy storage for long duration energy storage. Now, as you can see here, right, the bottom axis here is the penetration of renewable energy into the electric grid. Now, we are currently somewhere around 20 to 30% penetration of renewable energy into the electric grid. But if we have to fully decarbonize, we have to have tremendous penetration of renewable energy. Now, as we go to very high penetration of renewable energy, you can see that the amount of required storage goes up quite a bit. So if we have penetration of the order of 40%, you need only about a few hours of electrical storage to keep the grid stable. However, if the penetration becomes, say, like 80%, we are then talking about 10 to 100 hours of storage that is required. So the DOE is now has realized that trying to get this long duration storage, which is 10 plus hours, is critical to the national security and to the economic well-being of the United States. So unfortunately, to do this, you need very large systems, and the capital cost has to be quite low. So if you want to have duration of about 10 hours, the cost has to be about $40 per kilowatt hour. As you can see, this is again half of that of the EV batteries. And as you start going to more and more, the duration increases so that you can do seasonal storage. The cost has to come down to 3. So this is a very big challenge, and this is what is driving the fundamental research. And hopefully we will come up with solutions to deliver long duration energy storage. So the energy storage ecosystem develops as a whole. It is now clear that we need a diversity of battery technologies for a diversity of different applications. There are, and when we are doing this, we have to pay attention to the entire value chain, from raw material supplies to processing and manufacturing, to design of the battery packs themselves. And hopefully, because we do not want to keep mining all these critical minerals out of the ground, we have a good recycling component to it so that we can minimize energy usage and depletion of natural resources to mining. So all of this has to be, we have to pay attention to all of this so as to enable disruptive, transformative changes. If we are able to do this in the next decade or two, there are quite a lot of emerging applications where battery storage, whether it is aircraft, passenger flight, where you have to increase the energy density to about 3 times of what we can do today, which is quite a lot, right? Or we have to be able to stabilize against 10 days of consecutive cloudy or calm weather days, because when there is cloudy days, we might not be able to use the solar energy to convert it to electricity very efficiently. So we must have a storage as a backup for that. So both of these things require a lot of attention and a lot of science that needs to be done. So the core strength of my group is lies in sort of in the fundamental side to maybe very early stage TRL level 1 or 2 or maybe 3 level work. We have very good strength in material synthesis and scale up. Of course, we do a lot of battery electrochemistry. Some of the processes that are involved in this requires oxygen reduction or oxygen evolution reactions, and electrocatalysts play very key roles in allowing those reactions to take place. So we have expertise in electrocatalysis. We have expertise in processing within my group, as well as in a sister group, which is associated with with my division. Last month, we have very good expertise in recycling, and last but not the least, we do a lot of fundamental science, and to learn the operating batteries, what are the reactions that are taking place, what are the mechanisms underlying the battery phenomena in these materials, we do a lot of advanced characterization. So one of the key things that we have at Oak Ridge, which makes our work successful, is that we can make materials at the lab scale, which is typically about thank you. So
Their battery.
yes, or at least keep it charged, I suppose. Anyway, so thank you. We can make materials in the lab, discover new materials, which is of the order of grams when we make it, typically in a chemistry lab. But the phenomena and the electrochemistry that we do with those materials at this is often studied in small cells, which is like the button cells that we use in our watches and so on. They are called as coin cells. the chemistry that is learned from that, or the electrochemistry that is learned from that, might not be completely transferable to the industrial scale. So Oak Ridge has this facility called as the battery manufacturing facility, where you can make these pouch cell batteries, which are of the order of 1 ampere hour to 7 ampere hours, which are relatively large batteries, about perhaps 5 to 10 times smaller than what is used in car batteries, like in I don't know, a Nissan Leaf or something like that. But the science that is learned at this level, this pouch level, is completely transferable to the industrial scale. So this allows us to give this translation of research from the lab scale to the industrial scale, and a lot of activity around it takes place at Oak Ridge. And so we have been very lucky to have this facility, which is again funded by the Department of Energy. So I'm going to just go through very quickly few examples of the kind of work that the staff in my group are doing. And then towards the end, I will spend another 15 minutes or so on the work that I work with my staff directly on, which I'm more aware of, and I can perhaps make more justice to, I suppose. So one of the things, our core strength, one of the core strengths of our group is doing synthesis. And Rashid is an expert in synthesizing materials and scaling up materials after making it. So you can make materials of the order of, I don't know, 50 grams or so to do the initial test. And if the material shows good performance, then you have to scale it up to maybe kilogram level, and then use that along with the battery manufacturing facility to do a lot of testing to see how good this material is. And Rashid is an expert in it. Here is an example of how they manufacture this almost monolithic single crystal like lithium nickel oxide, which is used as a cathode material in this material, in lithium ion batteries. We also have other synthesis experts doing more fundamental work. There's a lot of work that is done on lithium ion batteries, but we also do other emerging technologies such as sodium batteries, which are useful for the long duration energy storage or the grid storage research. Monia Lee is an expert in synthesizing materials, novel materials, and here she uses a technique called as an eutectic method, where she mixes 2 or 3 components, and you can get them into the liquid state at a relatively low temperature. By doing that, she's able to get good atomic mixing in the solution state before she can make the cathode material. So here is an example of what she had done here to develop a sodium transition metal oxides. She couples this with things like gas evolution. When this battery is operating, she operando understands what are the gases that are evolved and what are the side reactions that are taking place. By understanding what is the side reaction taking place, she can then figure out what are the mitigation strategies one can do to suppress those side reactions. Alternatively, you can see if your cathode itself, how good it is. And that is the kind of work that we do. So these are some examples of the synthesis work we do. We also do processing. So you can take a standard material, and by means of doing different processing methods, try to improve the properties of this material. In this case, this work is on a solid state electrolyte, which was spearheaded by Mark. What he showed is that by a very straightforward process, using very moderate temperatures and pressure, you can stabilize this antiperovskite electrolyte in the cubic phase, which has very good electrochemical properties. This material normally is not in the cubic phase at room temperature, but by coming up with a new protocol, he was able to stabilize this material in a phase that would have very good properties as a solid electrolyte. So this is important because being able to manufacture materials and process it in such a way that it can be used in real devices requires fundamental understanding of the process. And this is an example of a work that MARM did, along with others. So in order to, as we said, one of the things that we need to do is most of the solid state batteries that are there now usually is made on devices which is of the order of maybe an inch or 2 inch in diameter. So these are relatively small devices which cannot be used for to deliver a lot of energy. In order to do this, one has to come up with processes where you can make large format devices. And so we have a program trying to understand processing methods to create solid state batteries with large format sizes. And one of the work here which is highlighted is again championed by MARM, where he has used this technique called as isostatic pressing, hot isostatic pressing, in collaboration with an external company to advance the processing method of solid state batteries. So solid state batteries as such is in an infancy, and we need to figure out how to make good batteries and what it requires. Most of the batteries in typical implementation at the research level, where you find out fundamental properties of the batteries, is on a device which looks like this. In this, the cathode active material, the positive electrode is this little portion here, and the solid electrolyte, which is just something that separates the anode and the cathode and allows the ions to pass through, dominates the mass of those batteries. But in a real device where we want to have high energy density, the batteries have to look more like this, where the cathode occupies most of the volume. We have a very small solid electrolyte and a very, very small negative electrode, which in this case would be a lithium metal in the case of a lithium ion solid state battery. To do that, one has to figure out what is the engineering parameters and what are the components that can be put together to make a good battery. And for this, MARM came up with this tool called as the Solid Pack, which is an interactive tool, from which you can figure out what is the material selection and what is the criteria required to get good energy density. This work was highlighted by an R&D 100 award in 2022. So in addition to that, I just said that we think that solid state batteries are much safer than lithium ion batteries. However, even in solid state batteries, people have now realized that when you try to cycle a solid state battery, you're trying to take lithium from one side and move it to the other side. Sometimes you can form these things called as dendrites. The lithium starts forming these filaments, which can penetrate even through a ceramic oxide. So and that is bad because you can short circuit the positive electrode and the negative electrode if the dendrite goes through the solid electrolyte. And that is a cause of release of energy, sudden release of energy. So to understand this and to see if there are mitigation strategies, Ruhul Amin and a student from UTK, Anand, worked on it. And they have come up with an electrochemical way by which you can heal dendrites that go into the solid electrolyte. So by passing very small currents with using a very particular electrochemical protocol, they have figured out ways by which you can make these lithium dendrites which have penetrated the solid electrolyte to disappear. So if this can become a standard protocol in real batteries, where if there is periodically, one can check to see if you have dendrites and try to wipe them out with a simple electrochemical protocol. So one of the things that I'm very interested in is to do characterization. And it turns out in all of electrochemistry, perhaps, and certainly in solid state batteries, the most important part of it is the interface. So as it's sometimes quipped, in batteries, the interface turns out to be the device. So if we can understand interfaces, whether it's an interface between the cathode and the electrolyte or the electrolyte and the anode, or interfaces within these electrodes, mastering them and controlling them can give us we'll then be able to design transformative batteries, because we will be able to design things at the atom level by looking at the interfaces. So in order to do that, one has to figure out ways by which we can understand interfaces and see how events take place. So recently we started a way of using confocal micron scale sensitivity X-ray fluorescence imaging at the APS, where we are able to look at the nucleation events between a solid electrolyte and a lithium. And this should hopefully allow us to expand this to do it in an operating operating solid state battery, where we can understand how detrimental events take place at this interface and hopefully come up with mitigation strategies for it. So solid state materials are used in other things. In our group, we have small projects on long duration energy storage. And this is an example of work where seawater is used in one side of the compartment and an organic electrolyte on the other side. And by using this, one can try to make a long duration energy storage device. On the cathode compartment, the reactions that take place are essentially oxygen reduction reaction and oxygen evolution reactions. And on the anode side, it's essentially stripping and plating of sodium, perhaps, or making sodium carbon electrodes where you can put sodium into the carbon and take sodium out of the carbon. So those are the kind of things. And this sort of a device, because you can do it with seawater, should be relatively cheap and should be very useful for grid storage when it is developed completely. Of course, you have in this thing, you have an organic electrolyte on one side and you have salt water, seawater on the other side. So these two things cannot mix. And in order to do that, you have to have a membrane, which turns out to be a solid electrolyte membrane, through which you can transfer the electron. However, it is very hard to get these membranes, which have good properties to both the organic as well as the inorganic, as well as the water, the aqueous as the non-aqueous portions of it. So tailoring these solid electrolyte membranes is a very productive area of research. So Monia has been doing that. She has made a device made of this so-called Nasicon electrolytes, where she has shown significant improvement in properties by just adding titanium dioxide to it. So this was an extensive work which was published recently. So we do a lot of work on processing. Most of the current day batteries, not all, but most of the processing that is done to make these large electrodes involves using slurries that are made of organic solvents. It's expensive to do it, and these organic solvents tend to be carcinogenic. So trying to get processes where we get rid of organic solvents is a good thing. And Zija has come up with this marvelous idea where he has been able to use high speed, high energy electron beam process to make these things using this process called as e-beam curing. So again, this was an excellent idea that came from our group, and Zija and the colleagues over here got an R&D 100 award for this technology that was developed. It's being currently licensed to an external company. So in addition to that, we discussed about fast charging, the need to be able to charge a battery in about 15 minutes in a car. So there's a lot of work that's going on in developing fast charging technology. And one of the ways that one can improve chargeability or the rate of charging is to tune the electrolyte that is there. So the electrolyte, which is basically a conduit for taking a lithium from one side of the cell to the other side. So it should have good properties to move this lithium. So ionic conductivity, lithium ionic conductivity, and ionic conductivity and lithium transference numbers are important properties that can be tuned. Additionally, it turns out that most of both the cathode and the anode are not in their thermodynamic state. They are all they are far away from thermodynamic stability. And the electrochemical stability window of the electrolytes do not cover the entire range over which it will be stable. So there is a lot of interactions that take place between the electrolyte and the electrodes. So tuning that also helps in keeping a pristine or keeping a good electrode electrolyte interface. So the electrolyte plays key electrolyte engineering is key to getting good batteries, particularly fast charging batteries. Zija has been very successful in developing batteries, electrolytes for fast charging, which meets or exceeds the requirements for the requirements put forth by the Department of Energy. So the another area of work that we are doing, and we do a lot of it actually, is in recycling. So the DOE is funding a large consortium with 4 national labs, Argonne, NREL, Oak Ridge, and INL, to work on this problem of recycling lithium-ion batteries. So recycling, as you can see, there are 3 different approaches to do recycling. There is the pyroprocessing recycling, there is hydrothermal processing recycling, and there's a third process called direct recycling. The smallest loop among these 3 is the direct recycling, where all these stages where you have mining, refining, and cathode production is taken out of the loop. So once the material comes through this loop, afterwards you try to recycle it without going through this cathode production or the downstream processes. By doing this, you save a lot of energy because it's very energy intensive to do these things. And we minimize depleting critical minerals that we need for this process. So there's a lot of work that's being done in this direct recycling within this R&D center, and Oak Ridge is playing a critical role within this R&D center. Here is an example. This work is led by Yoshai, and what they have figured out is that when batteries are made commercially, there is they make these large rolls of these electrodes, but there's a lot of waste because the edges of the electrodes are not used. It's only the central part of the electrodes that are used. So there is what they call as scraps. There's a lot of these anode scraps, which has the pristine material in it, unused, that is available. So in future, when a lot of the batteries, a lot of our cars become driven in using electric propulsion, there will be at some point a lot of batteries that have to be recycled. So currently there is a lot of demand, or there is a lot of need to recycle scraps. And when there is a mass deployment of batteries for electric vehicles, there will be a need to recycle batteries themselves. So with regards to this anode scraps, what Yosha has been able to show is that by a very simple process, which is not very energy intensive, essentially treating it at water at 60 C, the active material can be separated out of the current collector. All the materials that is there in this thing is fully recovered. So, and with a very simple processing, this can be again recoated onto another electrode, so the material can be fully recovered. And this is like this shows the electrochemistry that you get for the baseline anode, that is the virgin material, and the recoated anode, which is reclaimed from these scraps. And you can see that the properties of cycling properties, electrochemical cycling, are more or less is basically identical. So this is a direct recycling and remanufacturing of battery anode scraps. This technology was developed here by Yaoshai and co-workers. So similarly, we have a very good program on cathode direct recycling as well as hydrothermal recycling. This is an example where using a polyol metallurgical approach, using a citric acid as the reducing agent, they have been able to develop this method to recover cathode materials out of spent cathodes in this case. So this work was led by a postdoc, Lou, and supported by Yausha and Elias. So the last part of this talk is the work that I'm more directly involved in. I'm part of the other programs, but this I lead as a PI working with others. In this program, so far we talked about materials which use nickel in them for the lithium-ion batteries, but we want to minimize the amount of nickel and increase the amount of earth-abundant materials such as iron and manganese. So the DOE has put a deep dive program called as the Earth Abundant Cathode Active Material Consortium. It is led by Argonne and has over 60 researchers from 7 different national laboratories and 8 universities. And we are making a concerted effort in this to develop earth abundant cathode active materials, which can hopefully lead to very sustainable battery systems. So here is just a performance metrics that we want to try to reach. Essentially, the goals of this program is to reach about 400 cycles with about 80% of its energy retained after 450 electrochemical cycles. And the goals the DOE goals are to get 80 kilowatt hours and an energy target of 225. We believe that based on the materials that we have chosen as the baseline system, we should be able to reach 87 and 208. So in order to do that, one of the things that we want to do is to be able to improve the baseline materials performance at the so-called minimum rated state of charge. So we have to make this better in this region. So we are trying to understand how we can do that, and we are doing some fundamental science trying to figure that out. Now, the baseline material that is used is a lithium and manganese rich material. This material has a long history. It was discovered in the early 2000s, and there's a lot of work that has happened on this. It's probably the most promising material as far as to displace nickel-rich materials in the near future for transportation applications. So I'm going to give 2 examples of it. One is that I just said at the low state of charge, we want to control some properties so that we can improve the electrochemistry of this material. It turns out one of the properties we want to control is the low state of charge, what is called as the area-specific impedance. And we are trying to see if we can do this using doping strategies. The other one is more fundamental in work, where we are trying to see if we can figure out using a lithium-rich material, which is completely devoid of nickel or nickel in it. So we are trying to see if we can make materials based on manganese and iron. So I'm going to show some of the fundamental work we are doing in it. So here is the thing where we have doped this material with a small amount of tin. And as you can see over here, doping with small amount of tin changes the area-specific impedance at this relatively low voltages. That is the low state of charge regime. So if we can get good rates capabilities out of these materials at these voltages, we have to reduce the area-specific impedance to values which are of this order, around 20 to 40 ohm centimeter square. So we chose this tin because we know, based on the chemistry of tin in these lithium-rich systems, that tin would essentially go to this region which is lithium and manganese rich, and not go to these regions which does not have excess lithium. So we wanted to show that this is exactly what we have done with this material, and we did a bunch of characterization. First and foremost, we did high-resolution synchrotron diffraction, and we were able to clearly show that the tin, for very small amounts of doping, goes into the lattice. However, an interesting thing that we found is that for low values, the microstrain that is induces becomes quite high. And we believe that is actually a good property to have for some of the electrochemical things. So we show relatively high solubility of tin, and then most of the tin is present in this lithium and manganese rich regions. So to further understand the tin local environment, we carried out X-ray absorption spectroscopy, from which we are able to clearly show that the tin does go into manganese-like sites. And we also show that the local bond distances that are formed are elongated due to the presence of tin. And we believe that this local increase in bond distances causes coherency stress around regions where the tin is not present. And this is what is creating the strain that is seen in these average experiments that can be done with XRD. So to further confirm that, we did transmission electron microscopy, and we can clearly show again here that the tin is present in these regions which are near grain boundaries, which we believe comes because these local domains are trying to purify themselves of the dopants that we are putting, and it's pushing it to the grain boundaries. It turns out that doing this helps to reduce the area-specific impedance of this material. So we are continuing to follow up on this, and hopefully we'll have a better solution for trying to manage or mitigate the high area-specific impedance that is seen for these materials for low states of charge. The last example that I'm going to be talking is about this lithium and manganese-rich material, which is a cathode material made exclusively with earth-abundant materials. Now, if you do this material and look at it on the average length scale with X-ray diffraction, what we find is that it forms a layered compound. However, if you look at it with X-ray absorption, looking at the local structure around manganese and iron, we can clearly show that this material on a local scale is not homogeneous. So that there are these regions which are rich in lithium and manganese, and there are these regions, and by local regions, I'm talking of regions of the order of 5 to 10 angstroms, 1 nanometer like length scale. These materials tend to phase separate. So maybe the phase separate is not the right word. It's just that they are not homogeneously distributed. There is a lot of heterogeneity that is there in it. But this is fundamental to these lithium-rich materials, which we have seen in many, many systems. So one of the fundamental things we want to understand is when lithium is taken in, either put in or taken out of these oxides, what is charge compensating and how is the charge compensation process taking place? So there is a variety of methods one can use to look at charge compensation. And perhaps one of the most often used methods is X-ray absorption, because the absorption at the transition metal, the so-called pre-edge can give information about oxidation state and symmetry. But it turns out in the case of iron, the pre-edge positions coincides for a variety of environments. And it also turns out that whether the iron is tetrahedral or octahedral, the bond distances tend to be very similar. So you cannot use either the pre-edge or a measure of the local bond distance as a fingerprint of the oxidation state. So in order to understand that, we came up with a new approach where we utilize this, where we basically couple, where we use the spin-sensitive portion of X-ray emission and couple it with X-ray absorption spectroscopy to derive some information about the redox mechanism. And to do this, I just want to quickly show this. If you come with an X-ray of a certain energy, you can take one of these electrons, which is in the 1s level, and you can pump it into this so-called D manifold or the D bands that are present. So there are one of two things you can do. Typically, Hund's rule and Pauli's exclusion principle would say that you can have only 2 electrons and their spins must be opposite when they are present in the same state or same orbital. So it's often represented by this up spin or the down spin. So if you take the situation where the X-ray is able to populate a down spin, that is, you take this down spin from here and you put it into this d orbital, you reach an intermediate state which would be allowed because the 2 electrons would have spins which are opposite to each other. And then once that happens, the system finds this, because you have pumped an electron out of the K shell to a higher shell, the system relaxes. And one of the relaxation process for this is to eject out an electron from a P level to the S level. So that is a fluorescence photon that comes out. Now, so you can have fluorescence photon if you were to take this down spin and put it over here. Alternatively, you can do this process where you can try to put the up spin into this state. But when you try to put an up spin in this particular situation, because it is all the 5 electrons that are allowed in that level are all up spin, it is impossible to put this up spin over there. Pauli's principle gets violated, right? And so this process is not allowed for a D5 ion 3+ system. On the other hand, if you have an ion 4+, assuming an ionic model, and if you do the same thing, either take the up spin or the down spin, and in both cases, in this case, you will be able to do it because this level right here is empty. It does not have this one up spin over there. So one should be able to put this electron, both the down spin as well as the up spin electron. So one can do this by tuning the energy of the X-ray to exactly this transition where you go from this 1s level to the 3D level. And if you look at the spectra that comes out, in the case of the Fe3+, you don't see, in the case of Fe4+, let's start over here. You will see that there is a feature over here. So, and it is also there in over here. So both the spin state, one, the orange and the green corresponds to spectra you get for the 2 spin states. And there is intensity at this area for both the spin states. Alternatively, if you look at it for the Fe3+, there is no intensity here corresponding, like you see here for D5, because you cannot go to this, you cannot put this majority spin or the up spin state over here. So we figured out that we could use this as a mechanism to understand the ground state electronic configuration of the ion in this material. We have coupled this with other experiments like manganese XFs and iron XFs, and I think we have a full understanding of the redox process in this material. This was the first application of spin selective Zanes in battery science. So I'm going to just skip these things because this just shows how we did this for the other systems, and basically say that by employing this so-called high energy resolution fluorescent detection, we were able to get a holistic picture of the redox and structural behavior of fully earth-abundant, ion-based, fully earth-abundant, ion-based lithium and manganese-rich cathode. This work actually today got published, and it got selected as a cover for Chemistry of Materials. So it just came today morning. It's hot out of the press in some sense. So essentially, I hope I gave you a flavor of the kind of work that we are doing in our group. We try to envision, create, and sustain forefront research activities that can lead to transformative, cost-effective battery chemistries and technologies. Hopefully, this will enable disruptive changes to transportation and electric grid sectors. In order to do that, we need a wide range of science that needs to be done. So we innovate in material science, we innovate in processing science, we do a lot of interface engineering, we develop new battery architectures, we do battery recycling so we can have the cradle to grave, back to the cradle model of how we use these materials. And last, and hopefully this will allow us to develop new technologies. So none of this work that I presented here would be possible without the wonderful work and the contributions from my group members. I would like to specifically point out the early career staff who have been instrumental in doing much of the work, have been very important in bringing in new ideas. They have transformed our thinking intellectually. Marm, Monia, and Yoshai have played critical roles as early career staff. And these postdocs, CY, Anuj, and Lou, have also contributed tremendously to the effort that we have done. I should also point out that Nathan and Charles used to be in our group when I joined about two and a half years ago. They have moved on to greener pastures, I suppose, but their contribution has been critical in the early parts of the work that was done within my group. I would like to close with acknowledging. So we don't work in a vacuum at ORNL. We work very closely with the energy storage and manufacturing conversion group, which is within our section. We work closely with the sensor and electronics group, which is also within our section. We work with the grid system integration group who do a lot of power electronics, AC to AC conversion, AC to DC conversion, and so on. Eventually, if these batteries have to go to deployment stage, working there with them is going to be very important. All of these three groups are part of what happens within our division. Additionally, we work very close with the staff with the various battery programs in the main campus. We make use of BES user facilities. Here I have just pointed out the ones that are at Oak Ridge, but we use all facilities for advanced characterization, both DOE facilities as well as NSF facilities. And we work very closely with the staff in these facilities. Lastly, I'm very grateful for the funding that the group members have been able to raise to get from various sponsors. The Vehicle Technology Office, the AMMTO, Office of Electricity, Fossil Energy, ORNL, LDRD programs have been critical for us to launch new things. And last month, DOD programs, and last but not least, the industrial partners that we work with. With that, thank you for your attention, and I can take questions if there are any.
Any questions? When we look at grid storage as the technology exists today, do you have a figure on, for instance, what weight of lithium would it take to have 1 gigawatt day of energy storage?
I can't say offhand, but typically you get about 1 milliampere hour per gram on 5 microns of lithium. And we are talking of gigawatt. Okay, so you need a huge amount of lithium.
We've heard a lot lately about TVA considering putting battery storage in at the full run site. Is the technology really up to a massive battery storage system for the grid? Size of full run?
I don't know exactly what is the capacity of the bull run right now, but there are a lot of energy storage systems which are being deployed. There are things that are deployed, for example, for using spent lithium-ion batteries have been used to run small cities, for example, or things of the order of about 1 hour or 2 hours of energy required for that. We are nowhere close to large-scale deployment. There are technologies based on redox flow batteries, zinc-based aqueous batteries, and sodium batteries, which is being highly researched right now. There's also technologies based on iron, where you just convert iron to iron oxide and back. All of these technologies, hopefully, when they mature, should be able to help with grid storage. Right now, I mean, the storage is not, is typically only for of the order of few hours at the best.
And the other question?
Yeah, you talked about the length of time for a charge. I know that the current batteries, to get a relatively short recharge time, I'm not sure where it is on the low end, but you only charge it up to about 80%. At 80%, it starts tapering off. Is that sort of is that the assumption you make on these?
All of these things are for 80%. The numbers that we get, we get to see it's not 80%.
Is there any of this that your industrial partners are supposed to actually commercialize? Or can you say that?
I am not sure of which industrial partners are close to commercial. I think most of that is still in the research and R&D stage. There is a lot of work which is done on There is another consortium which our group is not part of, but the main campus folks are part of, where they are developing silicon-based anodes instead of carbon. Silicon turns out can hold more lithium in it than carbon. The problem with silicon is that there is a huge volumetric change when lithium is inserted or not inserted, alloyed with silicon. But companies have now figured out how to handle that volume. So that technology, if they can solve things related to calendar aging, there is a battery just sitting around at some state of charge for X amount of time deteriorates. If they can figure out how to get good aging behavior for these batteries, calendar aging, that technology might soon come to the market. So that is something that is being done in the DOE and has shown.
How many years until we could see a car with a 500-mile range with a 15-minute charge time?
500 miles range is quite high.
Yeah.
Sort of DOE is looking at as 300 miles.
500.
500 requires, in my opinion, at least, requires new chemistries. It has to go beyond lithium-ion chemistries. As you saw, the energy density that is required for medium haul vehicles, aircrafts, say going from, I don't know, Knoxville to Washington, DC or something like that. That kind of range itself, you need 3 times the energy density of what we have now. So your 500 is about twice what we want. To get that, you really have, I might be wrong, but we really need to come up with newer chemistries to do that. That said, if we can charge in 15 minutes, I think 500 miles is not bad. I don't think anybody wants to drive 500 miles at once. So if we can do that, I mean, maybe some of them do, but most of us don't want to.
Yes, you mentioned charging speed. What's the relationship between charging speed and battery lifetime or performance?
Very good question. So when you charge very fast, particularly with lithium-ion batteries, what happens is that the kinetics of lithium deposition on the graphite is the rate limiting process. So the lithium, instead of intercalating into the graphite, forms the so-called metallic deposits of lithium. So that is essentially you induce ore potential. So the effective potential is such that you can deposit lithium on the surface of graphite. So having this lithium, it then reacts with the electrolyte, and the lithium gets separated. So it gets separated from this process. So they call this as lithium inventory loss. So you have an X amount of lithium in it, and you start losing cycle to cycle as you fast charge and discharge lithium to it. The other thing that happens is that lithium tends to be very reactive. It forms these things called as mossy lithium, or they form these single crystal lithium, which shoots out of the anode as dendrites. So doing these fast charges limits, unless you can engineer fast charging so that you don't have too much of this lithium deposition in order to have life, right? You want to have these car batteries, you have to have 1,000 cycles or something like that. So if you have to get 1,000 cycles, then you obviously can't fast charge it 1,000 times. You might be able to fast charge it 50 times, right? But most times you probably want to do it in a more, more moderate rates. Of course, all of these can change, right? People are working very hard in trying to overcome these things of lithium plating on the anode. And the problem is you have to do this economically. You can't make fancy electrolytes, which have tremendous properties, which cost a lot. And the problem with these is we have to be able to make batteries that can allow us to make, so that these cars are not only for millionaires, it's for masses. And to do that, this is quite a challenge.
There are no other questions. We thank you. Okay.
Yeah, the battery recycling and manufacturing work, is that done on the Hardin Valley campus?
A
Or-
lot of it is done in the Hardin Valley campus. The main PI for that is E.S. Behuruk, who's a section head in my division, and Yao Chai and Lou and Rashid, they're all working on recycling on our end. There is also recycling activity in the main campus. Parantaman, who does something with brines. Shanghai does something. There are folks from separations chemistry who are working on it. So there is recycling activities in both camps.
And whatever happened to the lithium sulfur battery? I used to hear a lot about that.
It is still there in the radar. So for all these batteries, right, most of the batteries that I use today use a graphite or hopefully a silicon-based anode and a cathode. Before graphite-based batteries was introduced, lithium-based batteries were introduced by a company from Canada called Mahalingam. It turned out that, as I said, we were talking about the safety issues with lithium because it forms these dendrites and you can have these shorts. Solving the problem with lithium is key to do anything, including lithium sulfur. So that is the bottleneck. You have to, one of the bottlenecks that is there is that you have to solve the lithium problem, and then you have to solve the problem on the sulfur side. The sulfur side, there are two issues that one has to solve. At least two issues that one has to solve. Sulfur, when it forms these things called as polysulfides, lithium polysulfides, which are very soluble species in the electrolyte. So this, if it is very soluble in the electrolyte, this species from one side of the electrode, from the sulfur side of the electrode, can end up in the other side of the electrode just by diffusion process. And if it goes to the other side, then you can create the shuttle current where you make a polysulfide here and you do an electrochemical reaction on the other side and it comes back. So you are just transporting these polysulfides internally, and that creates a shuttle current which is not available in the external side. So that is a big problem with sulfur batteries. So solving that, and people have come up with a very ingenious way of trying to mitigate this or come up with ways of overcoming it. That is one of the problems with sulfur. Sulfur and the products are not very conductive. So the electrons do not conduct within the electrode. So improving the conductivity of that is important. So there are a lot of these sort of issues that has to be
That's a
overcome.
liquid electrolyte too?
It has,
A liquid.
most of it is liquid electrolytes. You can also do it with solid states.
Any other questions? With that, we thank you very much.